Yes, we will start in let some people join and we can start from there. So I think it's visible. Uh, so we can start our today's discussion, which is mainly focused on major points like the how the metering distribution should be done in the smart grid scenario, and thereafter we will be having uh, cyber resiliency of the smart grids, and after that we can have a brief discussion about the virtual inertia of the system, and later on we will be discussing some part of demand response, demand side management, or demand response program. Okay, so that would summarize this week's entire overview, and then we shall discuss some questions, and after that we will wrap up today's session. Okay, so mostly this uh, discussion, first of all, what is the need of the metering placement and how the metering placement impact the smart grid scenario. that we will be discussing first. So the purpose of placing the metering equipments all throughout the system is mainly led by the overall system association, that wherever each and everything or each and every part needs to be monitored closely, and that is the major aim with which we would be trying to uh, ensure that our cost is also reduced to some extent. And in the previous architecture, where the metering equipments were mostly emphasized with the RTUs in place, feeder terminal units in place in the distribution system, smart meters are also there nowadays. But the most important, or the, or we can say, the highly accurate equipment that can be taken care of is the PMUs. So that needs a dedicated research, or dedicated research domain is already there. So whenever you want, you can go through them, like the optimal PMU placement. So as we have previously discussed, that the need of metering equipments, how the need of metering equipments lays the foundation of distribution system monitoring and control, and also microgrid monitoring and control. So one of the basic aim is to have an overview of how the system state varies over time. So we need to have a close picture of how the system state varies over time. So for that, we need to have metering equipments all throughout the network, and based on these metering equipments, we can ensure that the proper monitoring activity is being done all throughout the network. So as I've discussed, that the RTUs, the feeder terminal units that we say in the distribution side, the smart meters are also there mostly. uh, yes, the major aim is to primarily, now these metering equipments, as we know from the principle of central limit theorem, that we already know, that we whenever we try to do some experiment, or do some experiment work, or rather, so what we generally do is to ensure that we take at least 5 to 10 measurements, and after that we try to aggregate them. So we take 10 measurements, and then we try to aggregate them, so as to get a better value. Means the value that we would get if we take just a single reading, then that single reading, suppose we are to measure 10 some 10 units. Okay, so these are not discrete values, so these would be digital meters which would be recording this any units, you can say. So for this 10, sometimes the meter reading would be like 9.95, 9.98, and sometimes it can be more than 10, 10.02, 10.08, etc., like this. So what we can understand is that here, if we take a aggregate of all these meter readings, so the average of these values would be more nearing 10. Now when we would be taking an infinite number of measurements, okay, so in those cases we can ensure that the values would be more targeted towards the central value, means that is to measure 10. So based on this, but here in the metering equipments, what we say, with aging effect, like we say aging effect, okay, now we can also say communication, because this data needs to be transferred from a location which is far away from the okay, video is on. So this communication needs to be done from the physical existence of the meter to the control center. So there can be communication channel delays, communication packet loss, etc. So we can consider loss. So mostly the transducers which measure some electrical quantities or other quantities, mechanical quantities to electrical entities, so as to deliver the digital information. So due to this, what we can see is that we have some transducers which also do age with time. So considering all these uncertainties, so these are called uncertainties. Okay. So with these uncertainties, what we can understand that the metering equipments that directly give the reading can't be trusted. Okay, because we are not taking hundreds of readings over time. What we can do is that, suppose this is the system under consideration, this is the IEEE 14 bus system. So let's suppose we have a meter here. Okay, just an example. So if we have a meter here, reading of, let's suppose this meter is an RTU. Okay, so we all know that RTUs can measure power quantities like the power injections, power flows, okay, as well as the voltage magnitude. So using these informations, what we can see is that, suppose the voltage measurement is erroneous. Okay, so what we can do is that here we have a metering equipment which is RTU. Another thing what we can do is that, if we ultimately we are to get the base operating states of the system. So base operating states of the entire system is required. So when we are required to find the base operating states of the system, which is V magnitude and the corresponding phase angle. Okay, so that we can ensure upon, and this is a real-time activity. Okay, so what we can do is that we can go for state estimation. And why is the term state estimation? We could have directly written the states that we can directly find from the metering equipments. The problem is that what the metering equipments deliver are not directly the states, or if they also directly deliver the states, what is in case for the PMUs, still they contain some metering but uncertainties that I have discussed here. Some uncertainties are still present in the measurements. Okay, so to to ensure that the uncertainties gets removed, to we can say to nullify the effect of these uncertainties, we can do something called state estimation. So using this state estimation or performing this state estimation activity, we would be getting the base operating states of the system, and as a result we can get, since if we can find the states directly from the states of the system, we can restructure the power operation, means from the states we can restructure again the environment, we can restructure and see the overloading, line overloading I would say. And of these activities can be seen that any side of the any part of the lines are overloaded or not. You can find out from the security constraint optimal power flow. So my point is that we can make sure that the states which we are getting are the best or are the optimal states. Now the cost of PMU, as we all know, is very high. So for the distribution system, which we all say that for the transmission system itself in the Indian context, it is not at all in its higher stages. It is in its budding stage, and we can make sure that we can implement them, or we can reduce the cost of these PMU someday or the other. But for the time being, the cost of the PMUs are quite high. The cost of the PMUs are quite high, and that's why we go for optimal PMU placement. So monitoring and control feature that we presently have needs to be enhanced due to the presence of more renewable integrated resources in the system. So although PMU installation is highly limited now because of its cost, in the transmission side only it is very limited. So since here we are mostly encouraged in placing the PMUs in the distribution system. So for the transmission itself, we go for optimal PMU placement. So in the distribution side, we also need to place the PMUs optimally, and overall cost should be minimized. So here's the PMU placement model that has been discussed, where the network data is being obtained and base case DCOPF is performed, and based on the true results, which ensure that the state estimation constraints, observability constraints are met. The objective function is to reduce the cost of PMU installation. Okay, so using these, the optimal locations are found for the PMUs. So we are to minimize the cost of the PMU placement, and using these data, what we can see is that the optimal PMUs, number of PMUs that can be placed are 14 for the IEEE 14 bus, 7 for IEEE 30 bus, 39 bus system, sorry, 3 for IEEE 14 bus, 7 for IEEE 30 bus, 8 for IEEE 39 bus, IEEE 57 bus we need to place 11 PMUs, and for IEEE 118 bus we need to place 28 PMUs. So overall we can see that the network contains 14 buses, but only 3 PMUs can make the entire system observable, and this condition is not considering the case of redundancy. So if we want to consider the outage, so we also need to take other constraints like system outages and all these things. So if we consider these outages, so the number of placement of these PMUs might increase, will increase, not might, it will increase, because some lines could be tripped due to like this out of suddenly there is a fault, so this line is out. So in case of PMU is making observable, PMU placed here is making observable, this line making this line observable, that won't be the case now. The PMUs which will be placed here can only make this system. So if a PMU is not placed here, then the case becomes problematic. So for that case, those situations, what we see is that we also need to consider the constraints of outages, system outages, and a paper also many papers you can find that the optimal PMU placement position based research work has been performed, and some of the techniques are uh, like the binary linear programming. Also we have some meta heuristic approaches some graph theory, techniques, etc. So there are problems with the meta heuristic techniques. Okay, so some meta heuristic techniques can be like yes, but for the first purpose we need to have the integer programming, we need to have the knowledge of integer programming based techniques, but various meta heuristic techniques include genetic algorithm. We can also say so each and every technique has their advantages or their disadvantages. So that you can directly find in the lecture itself. So now that is the reason why the optimal PMU placement, the emphasis has been given to optimal PMU placement, so that the cost is a major issue, and alongside to it we have the time, we can say time of sampling is very high. That's why we need to reduce the cost and also take the advantage of the time of sampling. So since we are getting high precision data, also the precision is also high. Okay, so precision is also high. So over and out we can see that we majorly have many advantages, with the major disadvantage is cost. So and suddenly replacement of the entire architecture, replacement of entire architecture or the entire power system architecture, power system monitoring, and replacement of power system control strategies can't be done at one go. So what we can do is that slowly we can include one by one, and someday or the other in future we can see that systems can become observable using the PMUs. Not observable, but we can rather say fully monitored by PMUs. Nowadays, what we do is that alongside to these PMUs, the RTUs which are already present in the system, they as well as some PMUs, means what we see is that if we have, if here in this case 57 bus 11 PMUs are making the system observable, so some hybrid techniques, they include, let's suppose 50% of this total number of PMUs, and mostly RTUs, because they are already there, they can't be replaced at one go. It's a slow modification that we are trying to aim, so that's to make the system more accurate, or observability context would be better. In the distribution system also, In the distribution system, what we have is that we mostly have reduced measurements. These are the problems. Unbalanced operation. So, unbalanced operation, reduced measurements. Also, we have uh, pseudo, which are some load forecasts. So, where we can see that the pseudo measurements, these are load forecasts. The forecast itself contains uncertainty. So we can directly say that they itself are not the up to the mark. So the measurement measurement uncertainty is much high. So what we are trying to aim is to reduce the uncertain measurements. That's our aim. And in exchange, what we are trying to do is to incorporate measurements with high accuracy. And to deliver this high accuracy, PMUs are GPS synchronized, as well as precision is very high. That means uncertainty is very low. But the problem is that suddenly we cannot replace. So in exchange, what we can do, we try to place optimally. Therefore, enhance monitoring accuracy. That's the overall view of this optimal PMU placement section. So now we will be discussing more about a bit of cyber attacks or cyber resiliency. So first of all, what is cyber physical system? So we have the physical layer, which consists of the transmission system, transformers, generators, transmission and distribution system. So these things are already present, but what was absent is that a good communication architecture. So the smart grid that we discuss is a smart grid with physical layer plus information layer. So physical layer is existing. What we need to take care of this is the information layer. So to make the information layer, what consists of, mainly we are adding the communication or improving, you might say, communication improvement. So communication is a part of this. The IT layer is the upper part. So in between we have the communication improvement, we have the physical layer, in between we have communication, and on the other layer, which is the information exchange or the cyber layer. So the problem rises that the people who are working on these equipments or system, they are not that much expert, because suddenly we can't replace altogether the entire set of people who are there. So what we can do initially is to slowly we can replace them. So but or another way what we can do is to impart knowledge about these cyber layers and all these things. So otherwise what we face is that various cyber threats. So mostly the physical layer that we have, physical layer, generation, transmission, distribution, consumption, this was there. As I've discussed, information flow. Here is the communication network, where you have dedicated wired networks, utility wired network, wireless networks, regional data collective system, power plants, system data collection, substation automation system, power plant automation system, etc. So energy management system, supervisory SCADA system, AGC, AGC load frequency control. So entirely we have this cyber physical system. Now we have the equipments also placed in the cyber physical system, and these equipments are mostly uh, what we can say, these equipments are mostly placed in the physical system, but we have a communication layer in between, and from this communication layer what we can write. So in the after the communication layer, if the data gets somehow manipulated in between, so that would greatly impact the entire power system estimation or monitoring and control objective. And suppose we have uh, since we all know that the states that we, as we have discussed, so states that we have discussed, the those are voltage magnitude and phase angle. So if we get the voltage magnitude and phase angle correctly, then we can find out the power flows, line power flows, P, Q, etc., P injection, everything that we want. But if we have something manipulated, and these follow some non-linear equations, right? They follow non-linear equations. So impact of a small change might impact heavily on the other things, on the derived quantities, and from this derived, and we are decision making decision based on these derived quantities. So suddenly, if the breaker sees that the information that is being flowing through the line is crossing the upper limit or violating the upper limit or violating the lower limit, so it would trip the system. So tripping of the system would result in mishandling of the entire power system, because lines would overload. Suppose we have one line, line 1, then line 2, line 3. These are not 3 phase lines, I'm just saying line 1. All these lines are operating in parallel, carrying a load over through an entire area, over an area, through a distant location from the load center to the load center from the generating plants. So if some of the lines get stripped, if line 1 gets stripped, the overloading that would result in overloading in the other 2 lines, and in this way we would be following up into a cascading failure. So, and that is the major aim of these theft or these attackers. Major aim of these attackers. So what we would try to do is that, and we have some various test systems like test equipments like the uh, normalized residual test is generally performed in the control centers. Okay, so if the attackers need to design the attack vectors, these are mostly in the research phase now the attack vector design. So if attacker can design the attack vector in some way or the other, so that they can evade these tests, then the data can get manipulated. We have a layer of protection, definitely we have a layer of protection, but this layer of protection is not for the attack vector. If the attack vector is designed in such a fashion, it can evade, because there are multiple times these things have been seen. And this process is like, we will have to design the vector as in a multiple of the existing power information from the power information, because the attacker won't have the access to the control center. So what he or she would have access is that to the measurements, and based on the measurements they can approximate if they can approximate to design the attack vector in some way or the other, so that they can evade these normalized residual test. They can definitely attack the entire power system. So our major aim is to, and the as a control means, if someone is designing these control logics, so he or she might have the have at least these things in mind, that the attack vector can be evaded in these methods. So we'll have to be prepared in somehow or in a different way, so that the attacker won't have the information of the other part. Means if attacker might not, or rather would be not capable of thinking in that manner. These are mostly hidden trial methods, because the attacker don't have any information inside, and from the outside where these uh, control engineers or control system control engineers, let's say, or the researchers who are making this system operation engineers, making means designing equipments for this, or designing system human machine interaction interface for these control engineers, they should be uh, more prone to have all around efficiency of this system. Okay, so that the attackers cannot evade. So based on this, we have different components here, which are a part of the cyber physical systems, and that can be more prone to attacks. Okay, so here we have the inverter nodes, we have storage systems, processing central equipments, the plant actuators, all these things. If you can manipulate, so there are types of attacks, that is false data injection attacks. There is also denial of service attack. we can say DOS attack or FDIA. So here data gets manipulated, and here the access gets manipulated. So repeatedly, the control engineers who are sitting in the control station, they won't be having the access of the various equipments or remote equipment. So somehow or the other, the attacker needs to manipulate the entire operating system and create an ambiguity amongst the uh, control system people, that the control engineers, that the system is working fine, but the system would collapse in some way or the other. So we can also it's like spoofing. Also somehow can attack someone can attack the we can say the protocol is change protocol. So there are multiple protocols taking care of each and every equipment or data transfer from each and every equipment. There are protocols like 61850, which takes care of the RTUs, or we can say SCADA, remote terminal units, communication of these remote terminal units. PMU, we have C37.118. We have protocols like okay, these two, let's consider smart meter. We have uh, DRMS. And all these things, we have many as various protocols, and some attacker might attack these nodes also, these points also. Okay, so okay, so there are some benefits of using this smart grid architecture that we generally get is a two-way flow. Okay, so what we have already, we had the electricity. Alongside to the electricity, we have information exchange. Okay, so both electricity and information exchange. Also we have control uh, effectively, means when we can design the control system, we can design the control system more effectively, right? Also what we can do is that various smart features or enablers, smart features can be integrated to these smart grid enablers, which are the uh, which you can say the distribution, the transmission side distribution. Hello, hello, hello. Yes, you can say some. You are not audible clearly. You are not audible. Can you please type? Can you please type? You are not audible. So I would request if you can please type. So there are some drawbacks like these cyber attack. Communication failures are also there. So these are the type of attacks that we generally go through in mostly these market architecture. Sorry, your voice is not clear. So if you can please write in the comment box, chat box. So here we have data manipulation attacks where FDIA is denial of service attacks, and FDIA is mainly affects the sensors, controllers, communication links, whereas the DOS or just a minute, charger is not switched on. Charger was not switched on. So here it is a man in the middle attack, and also we have the suspend the communication. The communication gets suspended based on these attack models. So uh, that's a basic difference. So these are mainly part of the cyber attacks and how we should make this cyber this entire smart grid cyber secure. So what we can do is that we can protect the system from the security perspective. Okay. Now the other term is cyber resiliency. So already some attack has happened. Now we'll have to already damage is done. So we'll have to compensate somehow or the other for those damage, or compromise has been done. So we'll have to compromise something. How are we prepared to this model? So that comes under the category of the resiliency. Okay. So we'll have to how much preparedness we are or do we have. Okay. So based on this, we need to at least have some uh, preparedness. Okay. So one way to get things prepared is to this is the anomaly detection. So we have some various cases. Now the things have become much more complex. Okay, with the integration of DERs, things have become much more complex. So I would rather say that sudden load sudden load changes or generation changes. This has become a basic part of the entire power system nowadays. Okay, so when we are having the information of load changes, that definitely it means that we have the some loads, because everything is done on the forecast basis. So since we have a forecast being done, forecast itself contains uncertainties. Now the wind or solar, they have some kind of uncertainties prevailing in them is based on this forecast. So forecast can't be accurate. So what they lead to is that there can be sudden mismatches, load generation mismatches, and we need to properly detect them. Okay, the sudden generation load mismatches, we need to properly detect them. So that comes under the broad area or the under the spectrum of anomaly. So anomaly not only considers the attacks, we need to detect the attacks accurately. Also we need to and prevent. Major aim is to prevent the system from getting attacked. Again, on the other hand, we need to detect bad data and also prevent the bad data from further usage into the monitoring aspect. So you need to detect them. And again, on the other hand, we need to detect sudden load generation changes. So these are correct. This is correct. Sorry, not these are. This is correct and should be allowed. And these and these are not required because they would result in inaccurate monitoring and control. So these two things should be prevented at the very beginning. So for that purpose, the anomaly detection technique should be accurate enough to prevent the system from getting damaged. So here are the means how an attack or how the system malware can compromise the power system, that the power system performance gets affected. But firstly, top level failure, physical consequences, cyber attack detected, attack technique. So malicious command to the exciter prime mover with referring from the SCADA system, and that would result in mal-operation of this generator or the alternator, and accordingly that would result in failure. So there should be more of proper anomaly detection techniques should be properly designed. Technique should be properly designed. So that's the major aim, and that can definitely, and that's the aim, and that can definitely help in the power system attack. So there are some approaches that we have already seen, but I will just to uh, wind up view of some centralized approaches where we can see the state estimation, chi-square test. Okay, then we have residual base detection, etc. And on the decentralized scheme, decentralized approach is with the singular value decomposition, etc. So these cyber attack models should be properly designed and developed before being enabled in the power system architecture, because these cyber attacks should be initially detected and prevented. So now comes the other aspect. So now it comes to the other aspects of the distribution system or microgrid architecture, we can say, or distribution system architecture, smart grid architecture. Anyway, we can say that nowadays what we are trying to integrate is more of the renewable side, more of the renewable entities, because our major aim is have the to have the go green architecture. Okay, so we have a ambition of by 2030 we'll have to uh, reduce 15% of our global carbon footprint, and by 2070 we will have to, from the Indian perspective, we will try to restrict 100% of the global carbon footprint. So based on that, uh, how the uh, system inertia gets affected, that we will discuss a bit about in these two slides. So what's the need of system inertia? Let's first discuss that, because we have we have mostly integrated renewables, right? Now, whenever there is a generation load mismatch, so we know the system will start swinging, because we know the swing equation. So the rotor starts swinging, and this rotor, why it starts swinging? Because it it will have to it will try to meet that deficit, either meet that deficit or reduce its generation. So, but suddenly it's impossible. So what can be done? There is a mechanical time constant involved. Okay, so when we have a mechanical time constant involved, we'll have to give that much amount of time after the system gets shut down, or not shut down, we would say reduce its generation, or to meet the generation load imbalance. Okay, so therefore we can do one thing. We can do a this is the case for where the conventional system works. Okay, so since the rotor is rotating with a kinetic energy, so with this sudden deviation or sudden dip or rise, the rotor's kinetic energy when rotor tries to deliver this kind of energy to the electrical energy outside. But the problem is that by doing this, the rotor shifts from the operating angle. So the rotor starts swinging. And after the time frame which is being set by this mechanical time constant, it again comes back to its original operating position. And that too in a its operating angle, let's consider if it is del 1, so it comes to del 2. If it goes beyond that, it has a range that it cannot go beyond if such is the working angle presently, and this is the maximum del max that it can reach. So the problem lies is that if it goes beyond this one, then the machine would be desynchronized at its very point, and less than that it will swing and swing, and after swinging for a time being, it will settle to its neo delta. Okay, so the problem now has become that with more renewables in place, and mostly solar, which mostly the solar is around 25 to 27% of the total installed capacity of India. So with this amount of renewable mix with solar is being more prominent. So we and solar don't have any inertia. It can only deliver active power. No system inertia present. These are static devices. At least wind do take part in their reactive power control, and we can take care of this. It can take care of this inertia to some extent, but the solar, which is mostly playing a major role here, and it has the absence of inertia. Now the entire system, which could have operated in a up, and with the increment, and one thing, with the increment in this solar, there's a reduction. With increment in renewables, there's a reduction in conventional generating scheme, conventional generators. So the problem now has become more stringent. That is, these generating units have reduced, so the system inertia is reduced, and on the other hand, the need of inertia is not reduced. So, because the load generation imbalances do take part, so for that, there comes the picture of virtual inertia. Although this is a mostly a research topic nowadays, with not much. Uh, yes, these are converter-based techniques where the converters energy, instantaneous energy gets transferred to the other side. The yes, the stored energy in the DC link. This gets converted to the or do take part in the inertia or ancillary support part. So what we can see is that previously this was mostly the control techniques were mostly centralized, but now it has become decentralized with more renewable being integrated with the battery energy management systems that we have previously discussed. These batteries do take a major role in maintaining the inertia. Not inertia, I would say. The batteries will have to play a major role because they can store the energy in need. So here you can see that which equipments can take part in inertia as well as active power control. So synchronous generator definitely it takes part. DFIG it takes part in active and deloading and corresponding mechanisms. So they can take part, but with the start. So this means synthetic inertia response possible with deloading and corresponding control mechanisms. PMSG same. PVRA here's a big no. Battery storage, yes, it can do both, like these synchronous generators. So another part what can be emphasized or that we will emphasize in the upcoming 3-4 slides is the demand response. So this is not in our hand. It will reduce. Our aim is to reduce this because of the carbon emission. Now PVRA cannot give inertia any way or the other, but the cost is low. The arrangements are easier. That's why we include more PV. So with PV increment, there's a systematic decrement in the conventional generators. Wind is also there. Battery storage, there has to be a second research topic which needs to be incorporated with the battery, that is regarding the second life of the battery. Okay, so these things are more complex, and but not complex, I would say. That would involve cost as well as uh, would say in the battery section we will have to think of the second life of the battery. Okay, so there are problems. So to ease out these things, some virtual synchronous generators are also being enabled nowadays, which works on the basis of various converters and inverter based techniques. So they also provide the grid stabilization. Okay, so like frequency regulation, etc. So so now we will discuss the demand response program that we have pointed out there. Okay, so we can discuss something about. In the meantime, if anything needs to be discussed, you can ask, or otherwise we can directly jump in the demand response program. Okay, so let's start the demand side management program. How the demand side management and what's the need of demand side management. So we can discuss a bit more about what is demand side. Now, as we have discussed that the people or rather we would say not people, consumer, consumer as well as the producer. So previously it was one line, everything was single line channelized. But now the consumers can also tell their requirement to the producer, and based on that, the consumers do take part in the demand response program. So one problem or one easy aspect is to convince the customers or consumers to take part in this demand response program. So producers, what's the aim of the producer? The aim of the producers or the generating people is to earn profit. Okay, so as their aim is to earn profit, similar is the aim for the consumer to have some profit. Otherwise, why to take such headaches? Okay, so in a way to uh, convince the customers needs to be incentivized. And what for and the background of this entire discussion is we have we already have discussed these things last discussion, weekly discussion, that we have a two-way peak, means the one is the morning peak, another is the evening peak. Okay, so our main aim is to reduce the morning peaks or evening peaks and fill the these are continuous plots. So fill the valley and reduce the peak, curtail the peak. Similarly in the evening. So our aim is to minimize the peak, reduce peak, and fill the valley. So with this thing in action, what we can say is that demand side activities can play a major role with the consumers posing their demands. So with the customers participating, now we cannot shut down a customer's fridge or AC from a distant location. That would be injustice. So we can't pressurize. So we need to channelize. So how we can channelize is we can take help from the system or help of these people and help them out in delivering better uh, feature to them. Okay, so we have this peak clipping. First, we have this peak clipping where the peak clipping, these are types of demand response programs or activities, I would say. So this is peak clipping where the peak gets clipped. Here's the peak gets clipped to a lower point, and with this thing, the or with this activity, with this peak clipping, the aim of this demand side program is met. Another one that we discussed is the valley filling. So we would be filling up this valley so that load curve is made flatter. And on the other hand, we would be minimizing this peak. Okay. So red means minimize, and Green means maximize. So maximize during this time and minimize during that time. So this can be also compared to load shifting. So this peak gets shifted to these points so that the valley gets filled up. Okay. Another is that the conservation, and on the other side we can increase the load growth. On the other side, flexible load can be reduced, increased, everything. So the necessity of these demand side management is to there are some necessities with fossil fuels are getting reduced day by day. So we need to preserve them for our basic needs. Also, global warming. So global warming has become a global warning. So we are to be warned. The environment is warning us that we should be minimizing our usage of these things. Okay. Also, renewables are very high. So we have previously discussed that with the renewables being very high, so here it is the duck curve. It is getting reduced day by day with the increase in the solar and solar device, solar plants, solar equipments, everything. Because during this period of time, the solar energy or solar generation is at its peak. So and the load is peak at its peak at these positions, but neither of solar wind is there, wind is here, and solar is here. Here solar, here wind, but load is here and load is here. So ultimately, if we cannot store them, if we cannot make usage of the batteries, so we cannot involve into this in these demand response programs. We have to have the placement of these batteries, so they can definitely deliver a better alternative. So there are some demand response programs like single objective and multi objective. So single objective and multi objective. These two demand response programs here mainly emphasized on the utility specified or user specified, either of utility or user, and this multi objective is for both. So 50% weightage would be given to the user and 50% usage weightage should be given to the utilities. So in both these techniques, our major aim is to reduce the peak demand, and by using these we can see that the peak demand can be transferred from one point to the other, as the demand peak can be shifted. So here we can see that this is the basic or no, not the basic, this is the this is the this is the demand load curve, and This is the targeted load curve. This is the generic. You can't. This is the approximated. So this is the target that if we can, for some area, if we can reduce this much to this much, that is enough, because we are trying to. This is the peak period. So overall, if area wise we can reduce the peak, ultimately for the total over throughout the day, if some areas also reduce, the some areas can reduce for some day or the other, and they can participate in these demand response activities, then altogether we can see a total shift, total demand response program would lead to power demand shifting. So same is the case. This is for the commercial areas. Okay. So after doing all these things, what resulted is that after performing these single objective based demand response programs, this is the single objective based. So what can be observed is that there is a shift, although that shift is not not have made the targeted value, but it's enough to reduce the peak. Okay, so the targeted, it has reduced the peak. So what we can observe is that peak gets reduced by around 500 kilowatt hour for, let's suppose, anyone. So similar is the case. This is for the industrial area. So this is the load curve, generic, and this is the targeted. So ultimately, as a result, there's a green curve which is delivering promising or better results than the, so which is delivering promising results when compared to the other load areas. Means the peak has flattened. So there's a significant reduction, 8,400, 8,500 to around 7,000. So 1,500 kilowatt around, approximately, kilowatt hour reduction. Okay. So this is for the commercial area. Now comes this is the single objective utility driven. This is for the multi objective DSM, where both industrial and whereas the sorry, multi objective means the utility driven as well as the consumer driven, user driven. So that also resulted in a better load profile. This is a very much aggregated value. You would not say that this much aggregated, but at least better than this one. So peak reduction at this ten, around 1,000 kilowatt hour. Here is also we can observe peak reduction around 1,500. With case of the microgrids also, DC microgrid, we can also see that the similar objectives. This is the forecasted load. This is the target load. So we have met, the system has met this much amount. So this is the demand side management program. So overall, as a result, it can be seen or it can be observed that overall reduction of uh, loading scenario, or say rather we can say the loading scenario, peak loading scenario, because we are trying to reduce the peak. So this can be observed with utility driven or customer driven. So utility driven, what we can observe, there's around 6.5% load peak demand reduced with the commercial, and for industrial there's around 6, not 6, around 5, sorry. Industry, user driven, or we can say customer driven. Consumer driven, we can say for commercial purpose there's a peak reduction of 6.2%, and for around 13%. So peak demand reduction is heavily impacted by incorporating the for the consumer driven part. And for multi objective, these are single objectives. For multi objective, it's around 10% and around 12%. So overall, what we can see is that in all these cases, in all these values are reduced values. And here, in case of industrial part, here also the systems have reduction. So peak reduction is observed for all these cases. So whether the system is being driven by, it's controlled by demand response management, demand response management is more towards utility driven or more towards consumer level, ultimately there's a reduction. There is a reduction in the total peak, and that is our aim. Demand response management. The aim is to reduce the peak. Okay, peak demand. So with this, we can discuss a bit of the demand response. So demand response can be considered to be a part of both the utility as well as the we can say both the utility as well as the consumer part, which the DSM or demand side management is mostly performed in the utility level. So but the demand response is performed both in the consumer level and the utility level. So ultimately, the major aim of peak reduction can be achieved within both of these cases. Okay. So what we can see with the aim of demand response, minimizing the total electricity consumption. That we generally we can see that the total reduction in the electricity can be observed. Okay, reduction in total required. Why we are aiming towards demand response? For that, we can see that our aim is to minimize the total electricity consumption, reduce the total power generation, promote green and clean energy, elimination of line overloading. There are various people are doing research on uh, some protocol uh, conversion schemes to enhance demand response. Okay. There are various schemes, protocol conversion, all these activities. People are doing lot many research work on. These are mainly means or in the research phase right now. So, okay, so you can see that here is the distribution substation, residential, commercial, industrial customers, and one DSO. Okay, and ISO, independent system operator. There is the transmission side. And here is the aggregator. So aggregator discusses everything with the ISO, DSO, and with the customer side itself. So these aggregator, they have the knowledge of what would be the uh, present consideration. What would be the present consideration? That how the things would flow. And here is the energy flow, green line, and here's the communication line. Okay. So ISO would be delivering the demand volume, delivering the demand information. Okay, aggregator receives this information from the ISO. Now the aggregator will select the consumer to participate in this demand response activity. So that's the role of this aggregator, to select the consumer how they would participate in this demand response activity. So now with the interested customers, information of these interested customers in place, so what he or she would do, they would be optimizing the total demand, and we based on this the present using this after optimizing, post optimization, the updated demand is fed to the ISO again, because people have agreed to participate in the demand response. So that's the procedure. Okay, so in the demand response part we have uh, the industrial customers, the commercial customers, and the residential customers. So industrial customers do consume more. Okay, and these industrial customers, we have the temporal dependencies, mostly based on high precision should be done, because the industrial loads are highly uh, fluctuating loads or highly variable loads with majorly the demand or the capacity is quite high. Okay, now security issues should be also taken care of. In the commercial side, HVAC, uh, air conditioning, that is high voltage air conditioning is all there. So reduction needs to be done from this section. In the residential part, that is HEMS, home energy management system, So home energy management system is uh, mainly it is focused on the refrigerator, AC, heater, all these things, electric dryer, electric vehicles, etc. So there are conditions where the people are the information gets transferred from this TSO that if they reduce their demand by somehow this much or this much, then accordingly they would be incentivized. So that motivates these customers. Otherwise, what's the need? So quality of service, interoperability, scalability and flexibility, security. So these are the communication requirements. So quality of service, these are the communication requirements. Quality of service, interoperability, scalability, flexibility, security. So demand response, classification of demand response programs. So DR based control strategy, DR based on price, DR based on load. And from the control strategy perspective, we have centralized control, we have decentralized control. Based on price, we have dynamic pricing, incentivized or penalty based pricing. And on the based on load, we have task related and energy related. And demand response based on these strategies, control strategies. We have centralized control where the aggregators are solely responsible and all the distribution substation is delivering and the aggregator is communicating with the distribution substation and all the house would be communicating with the aggregator and in exchange they would be delivered that much amount of delivered based on that loading scenario that household they would be delivering that much amount of power. Okay. So this is the centralized scheme and on the other hand we have a decentralized scheme where the aggregators and the distribution system operators do communicate but also they communicate amongst themselves. That's done. But on the other hand, each and every house they also communicate with each other. So they have communication from each side, both side. Okay. So they can interact amongst themselves. So this is the decentralized scheme and demand response based on pricing, dynamic pricing because ultimately we'll have to have some way or the other to reduce the customer usage or to reduce the peak. So should be ways out to how people should react to these things. So time of use, critical pricing, peak load pricing, real time pricing. So these are the various pricing schemes that would be encouraged uh, so that the people or customers do participate in them in this demand response. So mainly the task related to the demand is to based on the loading. So if the users are willingly participating in these demand response activities, so that would greatly affect the lifestyle. So if someone is having an EV electric vehicle, he or she needs to take care of this electric vehicle that whenever he or she is out of that out of station for let's say 7 days, 10 days, 15 days. So what he or she can do is that he or she can V2G vehicle to grid mode of feeding. So what he or she can do is that they can deliver that amount of energy or excess amount if there is some ample amount of SOC left so they can deliver that much to the grid and in exchange they can take the required amount or get incentivized to some extent by minimizing or reducing their annual charges or anything, or get payment in some way or the other. Okay, so in if someone violates, so that would lead to penalty. Not that everybody should try to follow a significant way that has been assigned, that is the optimal way, but somehow or the other people for people it becomes difficult. So in those cases people will have to pay the price, so pay more penalty. That is the aim. So communication architecture plays a major role. Okay, so and system should be entire demand response procedure should be unbiased. So with this, we have come to the end of this week's discussion. So any questions you can ask, or otherwise we will shift to some question answers. And this is the overall briefing of this entire week's discussion. Or otherwise, we will slowly start discussing the questions. So major parts that we covered: the optimal PMA placement, cyber attack detection, or cyber resiliency, or smart grid, inertia, virtual inertia, ancillary support, demand side management, and demand response program. Okay, so let's begin the question answer session for some more time, and then we'll wind up today's discussion. How many questions are there? Six questions. So let's start our discussion. So which of the following is not a type of classical optimization? Is not a there is an emphasis on not. So which of the following is not a type of classical optimization technique? Linear programming, mixed integer linear programming, binary search, non-linear programming. Any idea? You can write it in the chat box, or we can discuss, or we can see. You can speak up and give the answer, or you can write it in the chat box. Any guesses? Because this type of questions can come in the exam. So this is binary search. Okay. Lowest minimum number of PMUs to enable full observability. IEEE 30 was transmission system is 8746. Lowest minimum. No, you can say minimum. The lowest minimum PMUs to enable full observability for IEEE 30 was transmission system is. So this is the word of optimal PMU placement. So for IEEE 14 we have three number of PMUs. IEEE 30 we had 7 PMUs. IEEE 39 we had 8 number of PMUs. So here it is 7. Which one of the methods is exclusively and only a distributed detection approach? Distributed detection approach. So chi-square test, state estimation test, observer based, binary hypothesis based. Any more answers? Correct. So which one is correct? Please. So this is observer based. Okay. Which demand side management strategy is more reliable compared to the other strategies? Load growth, peak clipping, flexible load shifting. More reliable. Demand side management, DSM strategies, load growth, peak clipping, flexible load shifting, flexible load. Which demand side management strategy is more reliable compared to the other strategies? Load growth, peak clipping, flexible load shifting. So this is load shifting. So which one of the below mentioned DSM strategies refer to the load shedding events? Conservation, peak clipping, load shifting, flexible load. Refer to load shedding events. Refers to load shedding. Conservation, peak clipping, conservation, peak clipping, uh, load shifting, flexible. So higher load shedding means being observed. This is peak clipping. Energy management strategies in DC microgrid aim in energy management strategies in DC microgrids aim in increase the stress on the energy storage system, reduce the peak energy deficit, degrade the lifespan of energy storage, extract maximum power from PV and wind. From the DC microgrid perspective, what's the aim? The aim is to reduce the peak energy deficit. The critical difference between demand side management and demand response is DSM is performed at the utility level while DR is performed at both utility and consumer level. Utility level, both utility consumer level. DR is performed utility level. DSM is both utility and consumer level. DSM and DR are performed at utility and consumer level and at none. Any idea? So it is DSM is performed at the utility level. Which one of the following is not an objective of demand response? Minimize electricity cost, not an objective. Minimize electric cost, minimizing aggregator power consumption, maximizing the electric cost, and none of the above. Not an objective function. Maximizing the electricity cost. Okay. Which of the following holds the responsibility to provide AC reference bus voltage and frequency in an islanded AC microgrid integrated with battery, diesel generator, PV and loads? Loads, reference AC bus voltage and frequency. Islanded AC microgrid. Diesel generator. A diesel generator is capable of injecting active power only, reactive at the cost of absorbing reactive power only, and injecting both active and reactive power. So here it will be injecting both active and reactive power, which is not an objective function of demand side management. Peak reduction, optimal scheduling of generation resources, delaying the penetration of renewable energy resources, none of the above. Not an objective function. Please mind. Delaying the penetration of renewable energy resources. The wind turbine output power is processed through dash to feed the power to standalone DC microgrid system. AC DC and then DC DC, AC DC and then DC AC, DC AC and then AC DC, AC AC and then AC DC. So wind turbine output is processed through dash to feed the power to the standalone DC microgrid. So this side is DC microgrid, that is confirmed. So feeding a DC microgrid and going to generate sim AC. So AC to DC and then DC to DC. So this is correct. So with this we are done with today's discussion. So with this we have come to the end of today's discussion, and if you have any questions you can ask, or else we will meet on the next Saturday. Okay. Any questions? Okay, then we can disperse for today, and we will meet on next Saturday. Okay.